free boundary problem and interface problem. This is because I would like to talk more about methodology for solving this kind of problem rather than about particular problem. Also, I will present my recent studies too. How to manage centrifugal inducer pump here, inducer pump, here inducer itself, and here impact problem, slamming, deck slamming, and underwater vehicle moving in cavity with surface higher speed hydrofoil craft and cavitation on a hydrofoil. So even a cavitation in Venturi nozzle, here shown, the cavity appears in the Venturi, in this small diameter of Venturi, and then moving down with flow and collapses downstream. When collapse occurs, higher peak pressure appears and it affects the drilling bit too. It increases the speed of drilling and make many positive effects on the production. In case of a two-dimensional problem, the apparatus of complex variables is the powerful tool for solving free boundary problems. It is because any complex function satisfies the condition of fluid incompressibility and zero vorticity. The problem is to find such a function which satisfies kinematic and dynamic boundary conditions. Helmholtz first introduced complex variables for fluid dynamics, and Kirchhoff proposed conformal mapping technique for solving free streamline flows over the plate. The mapping technique requires to study basic complex functions, and then to heuristically to find such function which can transform plane of complex potential to the plane of the function zeta. Function zeta is inverse of the complex velocity function. Just considering how velocity change along the boundary, we can draw this shape of the region of function zeta. Function complex potential is quite easy. It is, for example, 0 at point C, stagnation point, and then phi potential increases along the boundary plate to B and further along the free streamline. So the complex potential plane is just cut with origin at point C and point D at infinity. So, and the problem is to find such a complex function which transform region zeta to the region complex potential. If we know elementary complex function, how they map their mapping regions, we can find, actually Kirchhoff found this transformation. It is quite restricted. Kirchhoff method is very restricted for solving the problem, because I explained it. It's difficult to find function which can transform one region to another region. So Mitchell and Joukowsky make a big step in the development methodology. They suggested to introduce upper half plane as a parameter plane. It is much easier to map half plane to another given region then two complex region one to another. So, and second, they propose to analyze region of the function omega, which is a Joukowsky function. It's a logarithm of complex velocity. And then when the function, when region of the complex omega and potential region are drawn, we can use Christoffel-Schwarz integral formula to determine the complex function itself. So this is big step. Now I show how to apply this technique in the example of flat plate. So using conformal mapping theorem, we can choose arbitrary position of 3 points. We choose B, C, and A, and point D at infinity. So then we draw the region of W plane. As I told, it is just cut in the with two sides of the cut, CBD and CAD. Then complex omega function has the following region. It's quite easy to draw this region because we have velocity magnitude real part and angle of the velocity as imaginary part. So we can magnitude velocity, analyze magnitude velocity and velocity direction. On the AB, velocity direction is 0. It's along the x-axis, and the velocity magnitude changed from 0 to velocity at point B, which is x unit equal to 1. Then we see that real part changed from 0 at point B to infinity at point C. If we go to the along the free streamline, the magnitude of velocity is equal VA, so this logarithm became 0, and only velocity direction changed. So we move from point B to point D and further to point A. At point A, we have the same situation. Velocity direction is constant, angle constant, and only magnitude change. So we obtain this figure, which is actually triangle. Then we need to apply Christoffel-Schwarz formula to determine these two functions. First, this is two angles. Angle C, at point C there is angle 2 pi, and point C is 0 position. And point infinity is not included in the Christoffel-Schwarz integral. So we have only one point. Substitute in this formula this value zeta and alpha equal to pi. We obtain this function. Derivative, differentiate and obtain derivative. Then do the same for the function omega. We have triangle, angle at point B minus 1 pi over 2 at point A. Again, angle at point A here, angle same pi over 2, and angle and point C 0 here, angle equal to 0. Two lines parallel each other. Substituting this value to the integral formula, we obtain this function. So so we can find mapping function as integral. So this is a completely equivalent to Kirchhoff solution, so it will be transformed one to another. And now I will start to talk about Chaplygin special point method. Before start to do that, I mention about two important things. First is, as you see, we use it half plane. And the upper half plane corresponds to flow region. The lower plane, half plane, is some symmetric region. So if we use, we will, in case of Chaplygin special point method, we will use not only half plane as a parameter plane, we will use different regions like first quadrant rectangle, so semicircle. There are many possibilities. It depends on the experience of the researcher which kind of parameter plane to choose. And in that case, we will need to extend the function obtained in the parameter region to the all parameter plane. So through the axis, through the boundaries. So here we need to, I would like to remind about symmetry principle. If, for example, we know complex function and point region R1, and we wish to extend this function to symmetric region R2, symmetric respect to the straight line sigma, and we wish to satisfy boundary condition on this straight line. For example, imaginary part of function should be 0. In that case, we can extend symmetrically function and into region R2, and we need to put at symmetric point P2 the value equal to the value complex conjugate value at point 1. If we wish to satisfy another boundary condition, for example, magnitude on this line, we wish to obtain magnitude of function constant equal 1. Then we need to put in the symmetric point value f function 2, which is equal this value. So, and provide also argument equal to argument at point P1. So this is first. Second, we will use Liouville theorem. It states if we know all zeros and polars of a complex function, we can build this function immediately. Because if complex function has no zeros and has no polars, then its function is just a constant. This is Liouville theorem. So if we unknown function z, and we know all zeros of this function and all polars of this function, then ratio of this function to this complex is just constant. So we easily find the unknown function. So Chaplygin singular point method, can you see it's more than 100 years ago. This special point method is based on the analysis of singularities and use symmetry principle and Liouville theorem. The method provides finding the required mapping function without applying conformal mapping technique in explicit form. This is, I think, this is a great achievement because sometimes Christoffel-Schwarz integrals are too complicated, too complex, and not easy to evaluate. So in this case, we choose the parameter region. Also, Chaplygin suggested to choose parameter region bounded straight lines and circle arcs in such way that its symmetric extension can cover all the complex plane. At the point of flow separation, the parameter region of the should form angle pi over 2, because we can see that this is complex velocity region for this problem, and we can see that point A and B, this region makes right angles. If parameter region have the same pi over 2 angle, then there is no need to introduce any singularity in the function of complex velocity. Mapping is conformal at this point. So this is example how to solve the problem. Same problem, this method. We choose first quadrant as a parameter region, and again we display points C, A, and B as we wish. And then unknown point D should be positioned, should be determined from the solution. So let's start to analyze complex velocity. For example, here. Complex velocity obviously has 1, 0, because velocity 0 is at the stagnation point. And there is no point in the flow domain where velocity is 0 or infinity. It means that complex velocity has only 1, 0 at point C, which is chosen to be equal 1. So, and again, order of this 0 is simple 1, because when we move around point C, an infinitesimal radius point C, then argument changed by pi, it is completely the same as in the parameter plane. So here 0 is the first order. So second step, we need to we determine it 0 at point C. Then we need to extend parameter region to the all parameter plane. Symmetrically respect imaginary axis, which imaginary axis correspond to the free surface, free streamlines, where velocity magnitude is equal 1, constant. Then, following the symmetry principle, we need to put at the symmetric point 0 of inverse order. So it means 0 polar of the same order. So to provide this boundary condition on the free surface. So you can see first is this 0, and here we put polar. Then it is easy to see that when zeta along real axis, just real value, it is velocity is real, and it can be 0, it's just real. Argument is 0 or pi, depending which psi is less than 1 or larger than 1. So plus unit or minus unit. So that is we determine complex velocity. We need to also determine complex potential or derivative of the complex potential. For this purpose, we analyze complex function. Actually, for convenience, we draw this function. I cannot see my point. Here. We draw the complex function, and we know that here, when we move along this infinitesimal small radius, argument changed by pi, while here argument changed by 2 pi. It means that here we need to put 0 of the second order to provide conformal mapping one near the point C in parameter plane and complex plane. Then consider point D. Point D is along the imaginary axis here, and when we when we move along infinitesimal small radius at parameter plane, it corresponds infinite radius in the W plane. And the direction is it is the same. So it means that here we have polar of the second order. Then the derivative will be in this point will have the polar of the third order. Also, we need to add a point corresponding to origin, because at point B we have angle pi, and in the parameter plane angle pi over 2. So transformation is not conformal here because of different angles. So it means we need to put here 0 of the second order in potential to provide conformal mapping near the point B. So again, we determined all zeros and polars in the first quadrant. Now we need to extend first quadrant onto all parameter plane. Such method to satisfy boundary condition of the complex potential, which is 0 imaginary part along the body and along the free surface, because problem is steady problem, and we have the same boundary condition on the free surface and on the plane. So we need to, according to the symmetry principle, we need to put singularities of the same order in the symmetric point. So what we did here. And that's all. We found complex velocity and derivative of the complex potential without conformal mapping technique in explicit form. This makes great help for solving free surface problem. So now we go further. The Chaplygin special point method applicable for solving problem of steady problem first, and for problem with straight and boundaries. So shaped body is not possible because we use constant value of the argument on some part of the parameter plane. So now we use the extend the Chaplygin special point for arbitrary shaped body, and for also for problems, for unsteady problems, when not only unsteady, in problems in which velocity magnitude on the free surface is not constant, like gravity flow, unsteady flow, and so on. So to do that, we discretize, again, we first quadrant as parameter plane. We discretize imaginary axis and real axis into interval psi I, psi I, and eta. Then we can, in that case, we have actually flow around polygon-shaped body with free boundaries where velocity magnitude change by step. It's difficult, maybe. If first is easy to extend imagine polygon, but how on the free surface velocity can change by step, it's not so easy. Anyway, we try to do that. So when we move around point psi I minus 1, the argument change delta chi. So we can see that we need to put singularity of this order into the function we are trying to find. It may be 0, it may be polar, depending on the value delta chi. It depends on the plus or minus. And then also we need to put it in the symmetric point. We need to put singularity of the inverse order, here minus, here plus, to satisfy boundary condition on the imaginary axis. Doing similar for the imaginary axis, actually it can be obtained from the previous discussion. For example, we introduce function g in order I. In this function, magnitude becomes argument and argument becomes magnitude. So we can apply same technique and obtain that this function has the same similar orders at point eta I. So now we can write the following function. Here gathered all singularities on the real axis. Here gathered all singularities on the imaginary axis. Then we use exponential form. In the exponential form, the product became sum, and sum in the limiting case became integral. So this is just this limiting case of this formula. So finally, we derived formula which can determine a complex function from its argument chi on the real axis and on his magnitude v on the imaginary axis. We use this formula later for solving the problem. Here shown integral formulae for the case when on the both imaginary and real axis of the first quadrant, we know argument of complex function, only argument on both axes. So we're doing similar as in previous, we can obtain this integral formulae. Here we can see here not big difference. Oops. Maybe.
Yeah, try to go on. Oh, no,
No,
really no.
So we obtained the same formula. And here application of this integral formulae for solving free boundary problems. It includes nonlinear steady free surface flow, water impact problems, and time-dependent problems in case of Hellischau flow. Now we consider relatively new problem, ice sheet liquid interaction in a channel of arbitrary bottom shape. Following assumptions are made. The fluid is assumed to be inviscid and compressible, flow is rotational, elastic sheet is enough thin to apply Casserat's theory of hydroelastic shell. Hydrodynamic pressure on the interface is the same as the pressure conditioning the bending of the elastic sheet. The obstruction may generate flexural-gravity waves extending to infinity in both directions. The flow and the shape of the elastic sheet don't change in time. That means we are considering steady flow. Flexural gravity waves is very popular topic in these days. A lot of papers published in linear and linear theories. Also, there are nonlinear theories. They are dealing with wave propagation on the ice sheet, response of ice sheet to moving load, and various heterogeneous properties of the ice, like crack, Polignac, Floyer, etc. So formulation of the problem is here. We need to find complex potential, doubles uz, which consists of two functions, potential and stream function. We introduce Froude number based on the depth of the channel. So the both potential and stream function satisfy Laplace equation. And we have a kinematic boundary condition, which is the constant of the stream function on the bottom and the constant but another value stream function on the interface. Dynamic interface boundary condition is written taking into account pressure due to bending, which conditioning the bending of the ice sheet, and there should be the same. So first we try to find derivative of complex potential, which in the present case is trivial job, because complex potential plane is just strip, and it is easy using just conformal mapping to find that complex potential is just logarithm of the zeta first quadrant of the first quadrant. So derivative of can be written also. And if we know complex velocity and derivative of complex potential, we can find mapping function. Again, the second more complicated but problem is that it is to determine the complex velocity. Here we write written boundary conditions. So argument of the complex velocity is given function. We assume that we know this function on the bottom surface. And velocity magnitude is given on the imaginary part, imaginary axis of the first quadrant, which correspond to the interface. We assume this, these two functions, velocity magnitude and slope to the bottom, unknown function psi and eta respectively. We will determine this function later. So we apply the integral formula derived previously and substitute here these boundary conditions and obtain the expression of complex velocity. It is almost the same, it looks like almost the same because we have no zeros in the velocity and we have no polars. This is and then we can write derivative of the mapping function, and we obtain such integral to determine the mapping function. Take bring your attention to this term, which is a logarithmic term. Formula are okay, but computation using this formula is not easy or not possible. This is because we need to consider long distance of the wave, long distance in the channel, but we can see that this parameter zeta grows exponentially as we move along the channel. So it's to make calculation, we need to change variables, parameter variables, using this equation. And then we can write the complex velocity and derivative of in this form. And here parameter became phi becomes parameter of this problem. Actually, we transform to the potential plane as a parameter plane. The solution includes two unknown functions, it is a function d beta d phi, and we can easily write this equation because function d beta ds is the slope to the bottom. It is given function. So s is the arc length coordinate is obtained based on the derivative of the mapping function and using previous expression. Finally, we can write the following integral equation respect to this function d beta df. It is a very friendly equation in terms of calculation because conversion is very fast and it does not take a lot of computational time. Most difficult problem is to determine velocity magnitude of the interface because the pressure on the interface depends on the higher derivative of the interface, curvature, and higher derivative of the curvature. So it is because of this difficulty we solve this, we satisfy dynamic boundary equation using numerical method. First, we consider velocity at node, discretize the interface, and velocity at v1, v2, at these are velocity magnitude at nodes. Then we can solve all the equation for the function, actually only one equation for the function beta, and we can compute shape of the interface. As we computed shape interface, we can approximate it spline to evaluate derivatives curvature and high derivatives of the curvature. Finally, we can calculate pressure due to elastic sheet, CIs, at node K of the interface, and determine the pressure from the liquid side. And this pressure should be the same. And it means that we have the system of nonlinear equation respect to unknown velocities on the interface. This problem is solved using Newton method for solving nonlinear equation. Before we continue with the results, we should consider dispersion equation, which gives us understanding what kind of solution we can obtain. Just differentiating Bernoulli equation, we can obtain this formula. Without elastic sheet, this formula becomes as formula this, and we know that Froude number is from the linear theory of waves. We know that Froude number equal to ratio of tangent hyperbolic divided k. So with elastic sheet we have this formula, and now we can equate in the right hand side and obtain characteristic equation. So this way does not require solving linear problem. We can obtain dispersion equation without solution of linear problem. So here is shown the solution of this equation for different thickness of the ice sheet. Without ice, this is solid line. We have wave numbers, one solution in subcritical channel flow, and the supercritical, but when we acquire the elastic sheet in present, we have two critical Froude numbers. One is the same channel Froude number, which equal 1, and another is the critical Froude number due to the elastic sheet. Below this critical number, we have no any wave any wave number. So for supercritical flow, in contrast of the without ice sheet, in supercritical flow Froude number, we have one solution for the wave number. This is a verification of the numerical method. We compare result without ice sheet with Forbes and Schwarz calculations. This is a famous work, very old, 1982, and fantastic how they computed this problem. Anyway, Forbes and Schwarz experienced the struggle with wave upstream. It is because they consider it quite a limiting distance of the calculation region. So in our case, we need to damp waves downstream and actually and upstream if they occur, for solving a problem for computing integrals. So you see in the previous slides. So in this figure are not shown the damping region, but the damping region in the distance 610, it's not shown here, but later in other picture it will be shown. What we can, because here aim to compare with the results Forbes and Schwarz, we can see we have no wave upstream. It's more accurate, obtained more accurate solution. And this is, sorry. Okay, this is subcritical flows, not shown subcritical flows. Froude number different 4, 5, and 6. What we can see is effect of the height of the abstraction. Abstraction is choosing semicircle as in Forbes and Schwarz. And here for Froude equal to 5. What we can see is that this is in this figure are shown. So there is a limitation in height of the abstraction to get the convergent steady solution. And in figure 5 is shown one set of subcritical flow solution for ice thickness 005 and different Froude number. So this is for Froude number 4, this is limiting one set case. For Froude number 5 dashed line and Froude number equal 0.6 dotted line. Actually the same. Okay, continue. This is a supercritical ice subcritical channel, supercritical channel subcritical flow. We can see that two modes of waves, elastic wave and gravity waves interact, and the result is superposition. This is a pressure and bending moment on the elastic sheet. The same results for the smaller Froude number 0.8. Oh, sorry, larger, maybe larger. Yeah, for smaller Froude number 0.8, it's closer to the critical Froude number, and here results very closer to the critical Froude number. We can see two complicated interaction of two waves of almost same wave number. So wave with the closer wave numbers produce very strong interaction. And here shown channel supercritical flow. If without ice sheet results are shown dashed line, and we have only this is perturbed flow, there is no wave, but with elastic sheet we have waves downstream. Here, the same result, but both smaller thickness elastic sheet. We computed a soliton solution for free surface flow without ice sheet, and but we cannot obtain solution corresponding to soliton wave with elastic sheet. Only previous slide was shown for dashed line, which is perturbed flow. So a conclusion, fully nonlinear solution of steady flexural gravity waves in channel with arbitrary obstruction is presented. Well, solution obtained in the form of integral equation. Interface shape between the ice sheet and liquid exhibits superposition of elastic and gravity waves. There is a region in the plane depth submergence, Froude number. Here, instead of depth submersion, the height of abstraction, Froude number, where steady solution cannot be obtained. Also, I would like to express my thanks to Isaac Newton Institute and London Mathematics Society, who supported my stay in the UK. Also, my gratitude to School of Mathematics of Mathematical Science, University East Anglia, as host organization for comprehensive support to research and a friendly community. Thank you very much.
Thank you very much, Yuriy, for the presentation. We have time for a couple of quick questions. If someone has one, even online, you can type your questions in the chat.
Can you calculate the waves in different levels before the obstacles and after, like hydraulic falls?
Hydraulic falls, actually, yes. With free surface, definitely it's possible to calculate hydraulic falls. But if ice sheet, in presence ice sheet, I don't know, actually. I did not try.
Any other question? Anything online?
Well, hello, it's John Ockenden here, Yuri.
So the applicability of all these techniques is that the fluid is incompressible, is rotational. So you cannot get rid of irrotation. You cannot point vortices.
Separate vortices is possible because if you have one or finite number of vortices, it's potential flow model applicable.
Yeah.
So it is the same.
But not a continuous patch.
Yeah, not continuous.
So Mark, is a big one.
Yeah, it's a very big.
Is it possible to extend the Chaplygin method to unsteady?
Yes, it is already applied for unsteady flow, but for Hellish-Shaw flows. Hellish-Shaw flows. I mentioned one picture, one paper. Here, last, free-bounded Darcy flow with surface tension, analytical numerical study. So here, unsteady, time-dependent, not only unsteady, time-dependent, because impact problems, water impact problems also self-similar, unsteady, but no time included.
Okay, I've seen there's a question from John Hall online. You can probably unmute yourself and.
Thank you. Hello, Yuri. Nice to hear your talk. I'm interested in your large Froude number limit because it is an exponential asymptotic problem when the Froude number becomes large. Did you hear me?
Sludge.
Speak up. Hello? Hello, did you hear me? Oh, good.
Can you repeat the question, please?
Oh, shall I repeat the question?
Yes, please.
I'm very interested in the limits when the Froude number is getting large in your channel flow, because it is a problem in exponential asymptotics. Do you have any comment on that?
What, Froude number is very large.
Yeah, when the Froude number is getting very large, it is an exponential asymptotics problem. You must use a very delicate asymptotic analysis, I think.
Maybe yes, in case of very high large Froude number, we will have one root of in the dispersion equation, and it will be. It means that quite small value. It means that wave length will be very large in terms of because it is in the channel. The slope of the free surface should be small, and maybe in this case we can apply some like asymptotic analysis, like shallow water approximation or so on.
My colleague John Chapman in Oxford has done quite a lot of work on that, S.J. Chapman.
Did you get the question? That John Chapman did a lot of work on the problem.
John Chapman?
Yeah.
I will read.
Okay. It's, I mean, like, we have people knocking on the door. So, John, if you can contact directly Yuriy and send a relevant reference, would be great. Thank you.
Thank you.
And, I mean, in the interest of time, we can all thank you again, Yuriy, for being a nice presenter, a nice author.
Thank you very much.
And I'll see you guys around. Thank you.
How long is this thing?